Hello and welcome to Inside Ophthalmology. This is Dr. Amrit welcoming you to another important lecture. Today we are studying OCT basics, and here we shall be focused on understanding the technology of OCT. So what is OCT? OCT stands for Optical Coherence Tomography. It is a non-invasive, non-contact imaging tool that allows for histology like cross-section images of the human retina. So this OCT is actually using the infrared light or near infrared light and measures the amount of optical reflectivity from the tissues. So what I mean by optical reflectivity is the amount of light that is getting backscattered from the retina. Now, as we all know that the light or the electromagnetic radiations are actually consisting of the ultraviolet, visible and the infrared light. The visible spectrum is from 400 nanometers to 700 nanometers, and anything beyond 700 is infrared. Using this infrared source of light, the OCT will actually create these infrared waves which will go to the retina, and then from the various layers of the retina they are going to get reflected back, and we are going to get image something like this, and this is what is optical coherence tomography. So let us briefly see about the history of OCT. The first concept of seeing inside the tissue started in 1971, and then we had in 1991 the first OCT image from the in vitro retina, and then from the human body, that means within the human body, in vivo retina was first imaged in 1993. The first commercial ophthalmic OCT device came in 96, and then we had the second generation of ophthalmic OCT in 2000. The third generation of Stratus OCT came in 2002. That was a time domain OCT, and then in 2006 and 2012 the spectral domain and the swept source OCT came, and finally in 2014 we have the commercial OCT angiography which was made available. So before I tell you in detail about the OCT, it is very important to understand the specific waveform. Now, as we know, in B-scan we basically use the sound waves which are also called the acoustic waves. So I have a video on B-scan basics. I would advise all of you to visit that video first. And whereas in OCT we are using near infrared waves, and these near infrared waves are nothing but they are the light waves. Now there are a lot of difference between the light and acoustic waves, and therefore there is a difference between the technology of OCT and the B-scan also. Before we understand the OCT technology, let me tell you briefly about the waveform. A particular wave is always made up of certain crest and certain troughs. Okay, so if you see this waveform, it is in a form of this zigzag waves around a horizontal line which is referred to as a timeline, and the positive deflection of this wave from the zero level is called the crest of the wave, and the negative deflection is called the trough of the wave. Okay, and the distance between two crests is called the wavelength, or it can also be the distance between the two troughs, that is also referred to as the wavelength of this waveform. One crest and one trough together, a crest and a trough together will form one oscillation of this wave. And what is meant by frequency? Frequency is nothing but the number of oscillations that will fit in 1 second in this waveform is called the frequency of that wave. Now the question is that why does this waveform get reflected back from the retina? It happens because of the difference in the refractive index of various layers of the retina. Since the refractive index is not the same, the light is going to get reflected back and backscattered, and that is what we are actually measuring. Now OCT is very much analogous to the ultrasound measuring. So in ultrasound we send the sound waves, and the sound waves will go inside the eye and they will hit the eye, and certain echoes will be certain sound waves will be reflected back, and these sound waves which are coming back, they are called as the echoes in case of B-scan. The echoes are measured directly in the B-scan, whereas doing so in an OCT is very difficult because the light waves will travel very fast. So we cannot directly measure those backscattered light that is coming from in a OCT technology. Now, so what happens is that we have this incoming light which will be traveling in the form of a wave, and based on the different refractive indexes of the layers of the retina, this wave will be treated differently by each layer, and then we are going to get signals from each of these layers separately like this. Now let me tell you something about the coherent and incoherent. Now what does OCT stands for? OCT stands for optical coherence tomography. So optical is nothing but the infrared light, and therefore we are calling it optical. And then there is a term which is called coherence. Okay, so what is meant by this coherence? So if you look at this second picture, you can see that there are 4 waves which are present, 1, 2, 3 and 4. And in all these 4 waves, you can see the crest of one wave is coinciding with the crest of the second, third and fourth wave. Similarly, the troughs are coinciding with each other. So such a waveform in which the crest will coincide with the crest and the trough will coincide with the trough, such waves are called the coherent waves. Okay, they are in the same phase. Okay, so what do we call them? We call them coherent waves. Whereas incoherent light beam is one in which the crest is not coinciding with the crest of the other wave. So as you can see, the crest is here in the first wave, the second wave crest is here, and again the third wave crest is here, and the fourth is here. So they are not coinciding with each other, and therefore such a wave is called an incoherent wave. Now, before I tell you about the principle of OCT, I would like to discuss something about interference. So what is meant by interference? When 2 waves of light which are traveling, okay, for a distance say x, okay, when these are combined together, they will form a resultant waveform, and as they combine together by traveling the same distance x, this process of combining is called interference. Now the interference can be of 2 types. It could be a constructive interference or it could be a destructive interference. So a constructive interference will occur in coherent waves. Okay, so what did I tell you about coherent waves? The crest is coinciding with the crest and the trough is coinciding with the trough. So when such waves will actually undergo interference, okay, what happens is that we will get a resultant wave like this. So if this was x and this was x, the resultant wave crest will be 2x and the trough also will get added up like that. Okay, so this is called constructive interference since they are getting added up. Okay, so there is a construction of a signal and you get a signal on the on your detector or on your screen. Whereas when 2 incoherent waves in which the crests are not coinciding with the crest of the other wave, we are going to see a destructive interference. Specifically, see, if this is x and this is minus x, why is it minus? Because it is below the, if you draw a baseline like this, so the crest will be above and the trough will be down, and you can see one crest is going to cancel the other trough. So because of that, we are going to see a destructive interference. So therefore we are seeing the straight line. We are not seeing any resultant wave. So whenever there's a destructive interference, we do not get a signal. We instead see a flat line on the recorder. Next is what is meant by coherence gate or coherence length. The reason you should know about coherence length is because the OCT is actually working on the principle of low coherence interferometry. Okay, so I told you what is meant by interference, okay, and then I told you what is meant by coherence and what is this low coherence interferometry. So for that you should know what is meant by coherence length. Now a wave will maintain this relationship of a waveform, okay, or a wave will propagate in the form of a waveform only up to a certain length, and that length is called the coherence length. Now what happens beyond coherence length is that the wave is going to undergo decay. Okay, the wave will get decayed, right? So in retina, because the layers are very thin and they're within some micrometers of length or width, we do not need a bigger coherence length for the waves, and therefore what we are using is a low coherence interferometry in which the coherence length is very, very small. So what is the principle on which the OCT works? As I told you, it is the Michelson's interferometry principle, also called the low coherence interferometry principle. So here we are using a low coherence light source, and that light source is basically being sent to a coupler, and this coupler is also called a beam splitter. Now this coupler will split the beam and send two signals. Okay, the one is going to enter into the sample arm and the other one is going to go to a reference arm. The sample arm is nothing but it is the eye. So one beam is going to go inside the eye and the other is going to a reference arm. So in a short while I will tell you what is meant by reference arm and why do we need a reference arm in an OCT. Now what happens is that the sample arm is the sample arm signal will go to the eyeball, and from the eyeball the light is again going to get reflected back and it is going to travel back to the coupler, and now it is going to go to this detector. Similarly, from the reference arm also you are going to get similarly a backscattered light, and these two waves are now going to reach the detector, and based on their coherence they are going to undergo constructive or destructive interference, and on the screen you are going to see an interference pattern, and finally you are going to see a display. On the display you are going to see a OCT image of the retina of the eye. So this is how the interferometry, very briefly, the interferometry principle of Michelson's. Now the question is, why do we need a reference arm? Okay, so remember this is the reference arm that I showed you. Why do we need this? This was not present in a B scan, right? But this is present in OCT. The reason is very simple. The light that we use in OCT, as we all know that light travels very fast compared to the sound, and calculating that delay of light. Okay, so what we're doing in an B scan is that we send these sound waves. These sound waves will get reflected from the surface. They come back as echoes, and based on at what time these echoes are coming, which is called the echo delay, we will calculate the distance of this path that the sound has traveled. However, the same thing we cannot do with light. We cannot calculate the light delay very as simply as we calculated the echo delay in case of the B scans. So here, what in case of the ultrasound, for example. So here, what's happening is that the backscattering of the light is very fast, and we cannot actually calculate it directly. So we do need a reference arm in which the optical path length will already be known, and using that we will calculate our we will calculate the distance of the layers of the retina and the thickness. So whatever distance parameters, whatever length parameters that you want to calculate, those can be calculated indirectly using the reference arms. So let us see how it works. So light from a low coherence light, as I told you, is going to a coupler, and the coupler is going to split it into two parts, a sample and a reference. The reference arm, the light will go back to will be reflected by a reference mirror, and it will return to the interference system in the opposite direction from where it came from. So as I told you over here, it's a low coherence light. From here, one is going to the sample, one is going to the reference. Here we have a mirror. As you can see, this mirror will reflect it back and then send it to the detector. Same thing will be done in the sample arm as well. So in the sample arm, the same process occurs, except that the beam will be now backscattered by the sample when the materials of different indices of refraction are encountered. Now this returning light beams which are coming, the one which is coming from the sample and the one which is coming from the reference, they are going to undergo an interference pattern. And mind you that interference will always occur when the optical path is traveled equally by both the sample and the reference arm. And since we have a reference mirror like here, and we already know this optical path length of this reference mirror, using the so whenever we get an interference signal, we know which length is present. We know the length already from the optical path length of the reference mirror, and the same thing we can interpolate to the sample, and that is how we are going to get the depth of each layer of the retina. So they both are going to undergo an interference pattern, which is going to be detected by the detector and then recorded. Now the important thing to know is that interference can occur only when two arms are matched in length, so that the returning pulses can arrive at the detector at the same time to interfere. Coming to the types and generations of OCT. The OCTs are basically two types, time domain and Fourier domain. Okay, the time domain is also called the TD OCT, which is also called as the first generation OCT. And then we have a Fourier domain OCT, in which again two types are present. The spectral domain, also called the ST OCT or the second generation OCT, the swept source OCT, the third generation OCT, or the SS OCT. Now this is how they are becoming more complex in the same order. Like the time domain was the oldest, and then we have the spectral domain, and then we have the swept source OCT. So what is meant by this time domain OCT? So in the time domain OCT, commercial OCT is the Stratus OCT, in which the light source that we are using is a monochromatic source of light. A monochromatic source of light is one in which there is only one single wavelength which is present, right? And usually the wavelength which is used is about 840 nanometers. Now it is called time domain OCT because there is a mirror, the reference mirror that I talked to you about recently. That reference mirror can actually move in a time domain OCT. And why does it move and how does it move, I will explain you in a while. So there is a physical movement of the optical length to scan various depth or layers of the retina. So what did I tell you? In the reference arm, we already know the optical length distance, optical length or the optical path distance of the reference mirror. And since the reference mirror is going to move in a time domain, this optical length is also going to keep on changing in case of time domain OCT. And therefore there is a time-based movement of the mirror, and that is the reason it is called time domain OCT. So this is a schematic diagram showing you about the technology of time domain OCT. So we have a low coherence monochromatic light source which goes to a coupler. The coupler is going to send a sample beam and a reference beam. The reference beam will go to the reference mirror. The sample beam is going to go to the retina. Now in the retina, every layer is going to get scanned sequentially using this reference beam as a reference. So let us see how this happens. So suppose first of all we have this monochromatic source of light which goes like this, and in such a way that, say this is the layer 1. At layer 1 only the crest will form, and at the other layer somehow only the troughs are going to come. So as we know that the crest is the part where the maximal intensity of a waveform will exist, so therefore you are going to get signal only from L1, that is the layer 1, because over there the crest of the wave is coinciding, and from L2, L3 you are not going to get any signal from L2 and L3. Now the reference mirror is going to adjust itself to this optical path length till we get an interference signal, and once we get this interference signal over here in the photodetector, we will note down the optical length of this reference beam, and from the optical length of the reference beam we will know the depth of this layer 1. So this is how the time domain OCT will work. Now after we know about L1, the machine is again going to send the same wavelength in such a way that now it will form the crest at L2, and then again a signal will come, and then the reference beam is going to adjust itself in such a way that we get a constructive interference at the photodetector, and using this reference beam distance we are going to find the depth of the layer 2, and we will get a layer 2 imaging. In this way, subsequently all the layers of the retina are going to get scanned. So you can see that how every single layer is sequentially getting scanned by the physical movement of this reference mirror, by the physical adjustments of the optical path. And that is the reason why time domain OCT actually takes time, okay? And the number of scans that we can do is also less. So it does about 400 axial scans per second, and the resolution is about 8 to 10 micrometers. So this movement of the mirror, by every time it is moving, it is actually creating an axial scanning of that section. So it does not measure or permit the visualization of finer retinal structure or pathology, particularly the outer photoreceptor layers the RPE, the choroid, and all that also. Moreover, it suffers from lower interscan repeatability compared to the spectral domain OCT. Since it is actually subsequent measurement of every layer of the retina, the process is actually slow, and moreover, the less attentive patient can actually move his eyes, because of which we can get motion artifacts. So motion artifacts are more in case of time domain OCT, and the resolution is also less, and therefore the images are also less sharp in a case of time domain OCT. Next, what do we have is the Fourier domain OCT. Now, the term Fourier is actually coming from the Fourier's transformation principle of physics. Now, I will tell you in a while what is meant by Fourier's transformation. But the difference between time domain and spectral domain OCT is that in time domain we have a mobile reference arm or the reference mirror. Here we have a fixed reference arm and a fixed mirror. So we are not altering the optical length of the reference arm. The reference arm optical length will remain same throughout the process of spectral domain OCT. The type of the source of light is what we are changing here. So there we use a monochromatic source of light, but here we are using a broadband light source, which is about 840 to 850 nanometers, in order to produce a spectrum of wavelength of the backscattered light. Okay, so we are going to use a light source which is 840 to 850 nanometers, and this is a broadband. A broadband means that it will actually send various types of waves of different wavelengths all at once, and every wave will actually choose one layer of the retina, and from that layer of retina the chosen layer of retina we will give a backscattered wave, and all the backscattered waves are going to be recorded at once. And this recording is not done by a very simple photodetector as we had in time domain OCT. We have a special high-speed spectrometer which is going to detect all this interference which is happening simultaneously because of projection of multiple waves from the broadband light source. Okay, and all these backscattered wavelengths are then going to undergo Fourier's transformation in order to provide multiple A scans with single exposure. Okay, so let me explain it to you in detail. So we have a broadband source of light, and this broadband source of light can actually simultaneously send so many waves of different wavelengths all at once. As you can see, they're sending green, yellow, and then there's a dark yellow, and then there's a red one in this diagram. So all are being sent at once, and then again they are going to be split just like we have in time domain through a coupler going into the reference mirror, and then they are going to send it to the sample as well. Now, similar to what happened in time domain, where the individual waves were going and getting reflected from the layers of the retina, here all the waves are going to travel to individual chosen layers of their choice. What I mean to say is, wherever, suppose this is a wave of X wavelength, and this will form a crest at L1, and this is a wave of Y wavelength which is forming a crest at L2. Similarly, so many waves are being sent which are forming the crest at different layers of the retina all at once, and therefore we are getting signals also all at once. So we are going to get this composite waveform which is so confusing. Okay, but the machine has a software which can convert this composite waveform into its individual frequencies like this, and this is called the Fourier's transformation. So when you actually see this, you might actually get confused as to what is this. This looks like a complete confusing mixture, but the Fourier's transformation can actually break this down for you and tell you the frequencies that this mixture is made up of. Okay, so this is what is Fourier's transformation. It is a transformation which will decompose a signal into the individual frequencies that it is made up of. Okay, so as I already told you that these waves are going to travel. So the green is going to travel to one layer, the yellow is going to travel to another, and the red is going to travel to another, all of this is going to happen in a single exposure, and because it is happening in single exposure, this is a very fast way of imaging compared to the time domain OCT. And therefore you can see the type of the amount of axial scans that are done are also in 10,000. So this number is actually, it changes according to the type of machine that we are using for the spectral domain OCT, but you can remember it as, if that was time domain was in hundreds, 400s, this is actually in 10,000s, and it is about 18,000 to 70,000 A scans per second. And the resolution also, you can see it has improved so much, it is about 5 to 7 micrometers. You can see the first image over here has so much noise, and this is a time domain OCT, and this is the spectral domain OCT with a much finer, crisp OCT picture that you can see with a much better resolution. So in time domain, the resolution was 10 microns, and here it is about 5 microns. Definitely the time domain OCT is more cheaper compared to the spectral domain OCT. Spectral domain is almost 50% more expensive compared to the time domain OCT. Then finally, the third generation OCT is the swept source OCT, which is also called time encoded frequency domain OCT. And the example is the Topcon's deep range OCT, which is the Atlantis. Here also we use the Fourier's transformation. Here also we have the mirror fixed. However, we are using a laser light. Okay, so all that broad band of light which had this green, yellow, blue, all that, it's all going to get collapsed into one single light, laser light. That laser light usually is about 1050 nanometers, and this layer, this frequency swept laser is a very tunable. Okay, it's a tunable frequency swept laser light. So let me explain it to you in a while. So instead of using a reference mirror to sweep through the layers of retina, we are using this broad range of frequencies, and these layers of frequency can change very fast because we are using a laser. Okay, unlike the spectral domain in which we are sending simultaneously so many waves, we have all this collapsed into one wave, and that wave can actually convert into different waves, but within a very narrow band. And that's why, because it is sweeping left and right across the spectrum of waves, this is called tunable frequency swept laser light source with an average wavelength of about 1050 nanometer. So the interferometric signal will be detected on a single small number of receivers, okay, as a function of time, and this will undergo Fourier's transformation and generate the A scan. So the Fourier transformation is much similar as the spectral domain that we have seen, and therefore spectral domain and swept source OCT both are called the Fourier's domain OCT. So as you can see here, this is the wavelength, and you can see this narrow line width. Okay, this laser can actually sweep left and right very quickly onto the layers of retina. So suppose this is L1, L2, L3. So what this laser does is it goes and hits here and see if it's getting a signal. If it does not get a signal, it will not go to the L2 but quickly change its wavelength very quickly at L1 itself and get a signal at L1. Okay, similarly it does that and at L2 also, where it is going to vary its wavelength very quickly, and same thing it does at L3. So that way it is sweeping across the wavelength using that tunable laser source. And then of course we have a reference mirror from which you get one signal, from the sample you get another signal. Both these two are going to get interfered at a photodetector, and then you get a interference signal like this that is going to undergo Fourier's transformation, breaking it into the individual frequency, and finally you will have your OCT. Obviously this is laser, so this is way too fast, so you are getting A scans in about lakhs, 100,000s. So this is about 4 lakhs A scans per second, and the resolution is 5 to 7 micrometer. This is about 5 to 10 times faster, and the signal is also excellent. Moreover, since you are using a laser, it can penetrate the deeper structures because the wavelength is also very large, about 1050 nanometers compared to the 840 nanometers that was there in spectral domain. So this can penetrate into the deeper structures. So your choroid and even the vitreoretinal interfaces, all of these will be more clear with the swept source OCT. So you can see this part over here is the imaging of the choroid. Okay, so this is the RP and the brux, and below that you can see this choroidal imaging, which is more clear with the swept source OCT. So let us see what are the differences between the time domain OCT, the spectral domain OCT, and the swept source OCT. So in time domain OCT, as I told you, there's a movable reference mirror. In spectral domain OCT, you have a spectrometer, and in swept source, you have a laser. The wavelength is about 810. It keeps on varying in different books. So 810 to 840. Spectral domain 840. This is about 1052. Okay, or 1050. The scans also, this is given differently in different books. So this is about in hundreds. This is in, you can say this is about in 10,000s, and this will be in about lakhs. So there are lakhs of scans or 100,000 scans per second. Resolution, if this is 10, 8 and 5, best resolution is in swept source OCT. So you can remember it as 5 microns, and this is also nearly 5. Lateral resolution is almost the same in all three, and artifacts are more in time domain. Obviously it is taking more time, so more time for patients to move and have deviated fixation. Because of that you will have more artifacts. Length of the line scan is 6 millimeters, here up to 9, and this is even more, about 9 to 12. So in one scan itself you can see the optic nerve and the macula together, okay, in one single line. So in my next video I shall be talking about the various types of scanning protocols in OCT, that is a macular line, and various additional scans. So stay tuned for the next video. If you like this video, give it a thumbs up and kindly subscribe to the channel. Thank you and have a nice day.